Say it again. So far, the number of partitioning levels was between log n and n. Okay, so the best case, log n, average case, log n, worst case, n. Now, this is the pivot where the pivot is always the first element. Now, in randomized quicksort, what happens is the best case becomes or stays log n. The worst case stays n, because the pivot is random, but we still might be unlucky. We always pick the smallest element. Let's say our random pivot, we are always unlucky, and we always pick the smallest element in the sequence. This could happen. Always pick the smallest. Obviously, the partitioning is going to have n levels. Okay, so the worst case is still n. Now, the average case is going to be log n with a very high probability. This is the only difference. When you have the normal quicksort, we say best case is log n, average case is log n, worst case is n. When the pivot is random, so the quicksort becomes randomized quicksort. The best case log n, worst case n, average case is log n with a very high probability. So the average case of randomized quicksort is much more better than the average case of the normal simple quicksort, where the pivot is chosen static. It's a static position. It's not random. So that's the only difference. Okay, but it is a very important difference. Now, why on average why on average the number of partitioning levels is log n with a high probability? This depends on probability laws. I tried to explain some of them in the slides. I'm not going to explain them in the lecture. These are for your own knowledge, okay? So we are using the result immediately from statistics. The number of partitioning level of quicksort when the pivot is chosen at random is log n with a higher probability. Now, in the light of this discussion, what is the asymptotic complexity of randomized quicksort? Okay, so can you tell me what is the asymptotic complexity of randomized quicksort in the best case, in the average case, and in the worst case? So what is it?
The worst case, it's big off and it's square. And big off and the worst case.
Okay, I'm not talking about the partitioning levels. I'm talking about the sorting algorithm complexity as a whole. So the worst case, yes, is big of n, which I have just said now. So I'm not asking you about that. I'm asking you now about the complete quicksort. Okay, so you have to multiply the number of partitioning levels with the cost of partitioning. So what is the asymptotic complexity in the best case? And the average case? In the average case? And the average case here is? Sorry, I meant the average of quicksort. This is for the non-randomized quicksort, and this is randomized quicksort. So the complexity of non-randomized quicksort in the average case is what? Is n log n, right? And here is, in the average case is the complexity of the quicksort. So this is n log n and this is n log n. So they are the same? Yeah, but here it's different. We have to say something more. It's n log n with high. Yeah, it's n log n with high probability. I mean, we have to say that they're not the same. Okay, this log n here is not highly probable. You see it sometimes on average. You don't see it other times, but here you will see it most of the time. In very unlucky cases, you see big O of n, but most of the time you are going to see big O of log n. That's why quicksort is the best sorting algorithm. It's better than merge sort. Even if it has a worst case complexity of n squared, and merge sort is n log n, okay? Even if it has a complexity of n squared, quicksort is still considered the best sorting algorithm, and that's because we rarely see n squared. We don't see it in practice. We don't see it that much. One thing. The second thing, it has a smaller constant factor. Compared to merge sort, it has a smaller constant factor. Because the partitioning is not like the merging. The merging of merge sort is more expensive than the partitioning of quicksort. Okay, so quicksort has a smaller constant factor than merge sort, and it has a worst case complexity of n squared with a low probability, and it has a complexity, an average complexity of log n log n with a very high probability. Now, if you get a question, this is not a hint or anything, but this is something that is going to help you. If you get a question about a sorting algorithm, what is the complexity? We have already seen the result. We have seen that a sorting algorithm can never be better than n log n. So if you see yourself writing something like the complexity of this sorting algorithm is log n, then you definitely know something is wrong. Okay? We said the sorting algorithm cannot be n log n. Okay, so you know there is something terribly wrong when you are writing that the sorting algorithm is log n or n. If it is a comparison-based sorting algorithm and you're saying it's n, then you are writing that the sorting algorithm is log n or n. If it is a comparison-based sorting algorithm and you're saying it's n, then there is definitely something wrong. Right. So, okay, remind me again of what are the problems of merge sorting. A high constant factor and what again? Extra space of which amount? Big O of n, right. So now quicksort, I said it has a lower constant factor, so it is better than merge sort. Now in terms of using space, is it better than merge sort? So in terms of using space, let's have a look again. Now, when I divide this into two parts, do I need a new space?
No.
Really? I mean, think again. This sequence is an array. An array is a contiguous sequence of elements. Now, take any partitioning operation in this table. Let's pick this one. I mean, look, this is an array. This is an array A1, and this is an array A2. Let's look at these elements here. 1, 2, 3. They are contiguous in my memory, right? In this array, what is 1 and 2 and 3? 1 is here, 2 is here, and 3 is here. So they were not contiguous, and now they are contiguous. So what does that tell you? What does this tell us is, almost, okay? What does this tell us is we have created a new space for these elements. We have this sequence, we have split it into two parts. As you can see, this is an array and this is an array. We have created a new sequence to put and put the elements 1, 2, 3. I mean, 1, 2, 3 are completely separate here. However, they are the same. They are close to each other here. So this tells us that we have created a new space. Okay, this is not like partitioning in merge sort. In merge sort, we can do indexes. We can say this sequence starts from here to here, because the sequences are always going to be, or the elements in the subsequences, they are always going to be next to each other. In quicksort, they're not. Depending on if they are larger than the pivot or smaller, they will move to a completely new subsequence. So this algorithm still uses an extra big O of n space. Is it clear why? No? No, it's clear. Now the question is, why did you say it doesn't use extra space? Because it's from our understanding of the array, we should be able to understand that elements in the array, they are not linked, okay? If they appear next to each other, the only explanation is that we have created a new piece of memory to hold them all. Okay? So that's how we reason about these things. So, again, this quicksort that we have seen has a worst case complexity of big O of n squared and an average case complexity of log n, and log n. If we make the pivot random, then we increase the higher probability of observing n log n at runtime. However, this quicksort or the randomized version of it, they are going to always need big O of n extra space. Okay. Now there is something I'm talking about in the slides, which is the median of medians algorithm. It's somewhere. The median of medians algorithm. You can read about this algorithm. What does this algorithm give you? It gives you, do you know what is the median? The median of a sequence is the element that splits the sequence into almost equal halves. So if you have a sequence 1, 2, 3, the median element is 2. If you have 1, 2, 3, 4, 5, 3 is the median element. So there is an algorithm called the median of medians, which returns to you the middle element of the sequence in big O of n time. Now, how can we use that in quicksort? How can this be useful for quicksort?
Using the random method.
How can that be useful for quicksort?
median very important or not?
This is useful in quicksort because instead of choosing at random, so we have a sequence. We call the median of median algorithms, and it tells me that the median element is at position, for example, here, and then I take that element as the pivot. If I take it as the pivot, then the left and right subsequence are going to be of almost equal size, right? And then I take that element as the pivot. If I take it as the pivot, then the left and right subsequence are going to be of almost equal size, right? Right? And then I apply the median of median algorithm here, and it gives me the middle element, which splits the sequence into two sequences of almost equal halves, and so on and so forth. So each time I am able to split the sequence into two almost equal halves. So what is, in this case, what is the number of partitioning levels?
Okay.
Is this the worst case?
No, the best.
Okay, so that's the best.
Average.
And average. So what's the worst?
The worst big
Why? The worst case is going to be log n, because I am using an algorithm. This algorithm is guaranteed to always return the median element. So this is like merge sort. So every time I am going to have two sequences of almost equal size. Okay? Each time, this is an algorithm, this is not random. Okay? This is not a random number. This algorithm is always going to give me the middle number. So the worst case is log n. It's always going to give me the middle number. So if I have my sequence 1, 2, 3, 4, 5, 6, 7, 8, and I want to sort it in reverse order, let's say, and I execute the median of median algorithm, it gives me number 4, let's say. It gives me 4. It tells me the pivot is 4. So I choose 4 to be my pivot, and I put 1, 2, 3 here, and 5, 6, 7, 8 here. Well, if it's in reverse order, it shouldn't be like that. 5, 6, 7, 8, 1, 2, 3, reverse order. And then I execute the median of medians here, and it gives me, let's say, 6. And so on. Okay? So I end up with the worst case of big O of log n. And I told you in the slides that this algorithm has the worst case complexity of big O of n. So what is the worst case complexity of quicksort if it uses the median of median? Yeah, exactly. It's n log n. So if quicksort uses n log n, if it uses the median of median, the worst case complexity is going to be n log n. Randomized, this is the one that uses median of medians. Randomized quicksort is going to have a worst case complexity of n squared with a low probability, and a worst case, an average case of n log n with a high probability. Now, which one do you think is better? It would seem so. That looks better than that one, definitely, in terms of complexity. However, it has a higher constant factor. Now, can you explain to me why it has a higher constant factor? Obviously, I haven't told you anything other than this explanation, but you should be able to tell me why it has a higher. Obviously, I haven't told you anything other than this explanation, but you should be able to tell me why it has a higher constant factor. I mean, compare the two. Compare randomized quicksort with the median of median. how are they different? Which part is different between them?
Medium change the element, not need to change the first element in the sort. Yes, but in the quick, we need to change the best and compare between the elements.
I did not hear you well. Can you say it again?
Medium,
Ah.
medium. We choose the median element, not the first element, but no, any element in the sorting. But in the quick, we have the first element in the sorting.
Nope.
This
Sorry, that's randomized quicksort. So we choose the element at random.
random.
Yeah, randomized. We said there is quicksort where we choose an element at a particular position, and randomized quicksort where we choose the pivot at random. Do you remember that? You're lost?
What?
Okay, let me answer my question because we need to finish now. Okay, quicksort, we choose the pivot at the beginning of the sequence, at the end of the sequence, at any position in the sequence. It doesn't matter. Randomized quicksort, we choose the pivot at random, right? We said that. Please tell me you did not forget.
No.
Randomized quicksort, we choose the pivot at random. Is this correct or not?
Yes. Yes.
Okay, we choose it at random. Now, so randomized quicksort, what does it do? It chooses a random pivot and then traverse the sequence in order to do the comparisons, right?
Yeah.
Now, the quicksort with the median of median, it does not choose a random pivot. It calls the median of median algorithm, and then in order to find the pivot, and then it traverse in order to do the comparisons, right? Choosing a random pivot takes big O of 1 because it's just a random number generation. Traversing is big O of n. Median of median is big O of n, and traversing is big O of n. So this one is still big O of n, but this one has a smaller constant factor than this one, because this is like 2n, and this is n plus 1 only. Does this make sense, or you're completely lost? Okay, if it doesn't make sense, remind me to repeat it next lecture, because we need to finish now. You have some negotiations to make concerning the midterm schedule. So see you next week.